Good morning. We are going to study our unit 4, that is the second part of solution of non-electrolytes. Now in this we are mainly focusing on the process of distillation. Distillation, it is commonly used method for purifying the liquids and separating mixtures of liquids into their individual pure components. Industrially, distillation it is a basis for separation of crude oil into various useful hydrocarbon fraction. Chemically, it is the principal method for purifying liquids. Successful distillation depends on several factors, including what is the difference between the boiling point of the mixture of the component of the mixture, and therefore the difference in their vapor pressure, the type of apparatus used, and the care which is taken during the experiment. Now, to understand the distillation, first we will consider what happens upon heating a liquid. At any temperature, some molecules of the liquid possess some enough kinetic energy which is required to escape into the vapor phase. We call it as evaporation process. And some of the molecules in the vapor phase they return back to the liquid state. We call it as a condensation. And when an equilibrium is set up, both these rates are equal. So, at higher temperature, more molecules possess enough kinetic energy to escape, which results in greater number of molecules to evaporate. The most common method of distillation are simple distillation and fractional distillation. Now, we will see this. Now, this is the boiling point composition curve. Now, this is vapor phase, this is liquid phase, and again this is the mixture of liquid and vapor as we have discussed in the previous lecture also. Now if we boil the liquid having the composition C1, suppose we have this. If we boil it, we will reach here, and the vapors which we get have the composition this one. If we condense these vapors, we will get the liquid here. Now, if I boil this composition, means from C1, I just boiled the liquid, collected the vapors, cooled it, temperature decreased. So, I will reach to this composition, C2. If I reboil this composition C2, again I will go here and the related vapors will have composition C3. So, the vapors are now richer like this in the more volatile. This is more volatile substance. As it has less boiling point, it is more volatile. So, we are moving towards the system having vapors richer in more volatile. We are reaching towards B. We have started from C1 and by these processes we reach to C3. If we do this once or twice again, we will come closer to this. Like this, we can able to collect the liquid which is virtually pure B. It is the secret of getting the more volatile component from a mixture of liquid. It is obviously to do the successive boiling, condensing, reboiling, condensing, reboiling, condensing. These are the steps, successive steps which we have to follow. This is about the phase diagram. And what happens in the lab? We use such type of fractional distillating column. The fractionating column, it is packed with glass beads. It is present, it is available in our lab also. It gives maximum possible surface area for vapors to condense back. So here the vapors will go upward, condense back, again go upward, condense back, and the vapors which are richer in more volatile, they will come across this path. They will be cooled and collected in this conical flask. The mixture is heated at such a rate that the thermometer is here. Thermometer of the boiling point, it shows the boiling point of the more volatile component. The bulb is exactly at the outlet. Now what happens in this column as compared to the phase diagram? Now we have boiled here at C1 the vapor over the top of the boiling liquid. It will be richer in the more volatile, and we have composition C2. Now the vapor now starts traveling up the column. Eventually it will reach a height of a column where the temperature is low. Temperature is enough low that the vapors will condense to give a liquid. The composition of the liquid will be of course now C2. Now what happens to that liquid now? Again it will start trickle down the column where it will meet now new hot vapor. This C2, it will come back and it will meet to the new hot vapor, rising its temperature, so that will cause the already condensed vapor to reboil. This will be coming down, but again it will be reboiling. Some of the liquid of composition C2, they will boil to give the vapor of composition C3. So let's concentrate first on the new vapor and we will think accordingly about the vapor. This new vapor will again move further up the fractionating column until it gets a temperature where it can condense. Then the whole process repeats itself. Each time the vapor condenses to a liquid, and this liquid will start to trickle back to the column where it will be reboiled by the upcoming hot vapor. Each time this happens, the new vapor will be richer in the more volatile component. The aim is to balance the temperature of the column so that by the time vapor reaches the top, after a huge number of condensation reboiling, condensing reboiling operations, it consists of only more volatile component. In our case it is B. Whether or not this is possible depends on the difference between the boiling point of the two liquid. The closer they are together, the longer the column has to be. Now we will think about the liquid. So what about the liquid which is left after each reboiling? Obviously, if the vapor is richer in the more volatile component, the liquid left behind must be getting richer in A. As the condensed liquid trickles down the column, constantly being reboiled by the upcoming vapor. Each reboiling makes it richer and richer in the less volatile component A, because vapors are richer in the more volatile B and it goes here. And the remaining liquid is now richer in A. By the time the liquid drips back into the flask, it will be very rich in A indeed. So over time, as B passes out of the top of the column of the condenser, the liquid in the flask, these vapors will become richer in B. They are collected here, and remaining liquid, these vapors are richer in B, but the remaining liquid, this gradually becomes richer and richer in A. Finally, what is the point of packing? To make the boiling condensation reboiling process effective, it has to happen over and over again. So to give the large surface area inside the column, maximum possible contact between the liquid and the hot vapor rising should be taken care. If we don't do the packing, the liquid would all of the side of the condenser, they will be there, and most of the vapors would be going up and the middle and never come into the contact with it. That's why we have to pack it. A very short narrow passage in which this tickling liquid and the hot vapor, they should come in contact with each other. Otherwise liquid will stick to the wall and the hot vapor will leave. So this should not happen. That's why the columns are packed. So we can draw all such graphs for first, second. I have seen 1, 2, 3, 4. We can draw so many graphs, so many steps. The number of the cycles, vaporization, condensation occurring in the fractionating column, it determines the purity. The efficiency of the column depends on the column length and the composition. In this column, column is packed with copper sponge. It increases the surface area for the ascending vapor encounters and result in more vaporization and condensation cycles compared to the empty column. Efficiency of a column, it is determined in number of theoretical plates of that column. One theoretic plate is equivalent to one vaporization condensation cycle. Thus, a fractionation column that can attain the equivalence of the three column, it would be how to say three theoretical plates. So to obtain the maximum efficiency, the distillation rate must be kept constant and slow. Distillation rate is a single most important variable that will contribute to an effective distillation process. Now, fractional distillation of non-ideal solution. These are the type 2, 3, showing minima and maxima. Azeotropic mixture, type 2 and 3. When the vapor pressure of a solution shows marked deviation from Raoult's law, the boiling point may show the solution has boiling point either lower or higher than the pure component. So fractional distillation of non-ideal solution, it exhibits minimum or maxima boiling point. It is only one of the constituent in the pure form, depending on the composition of the liquid mixture. Now we will see this. Consider the distillation here. Say we will consider a point x1 lying between this point. We can see from the diagram that it is divided roughly into two parts. Suppose our composition lies this side, point x1. Then the liquid mixture, it will start boiling at temperature T, and the vapor which appeared on boiling will have composition Y1. We are boiling the liquid, we reached here, vapors are Y1. The vapor phase carries relatively more of the constituent of A. Liquid carries more of B, vapor carries more of A. It is obvious that the remaining liquid, this will contain more of B, and it will boil at higher temperature. As the distillation proceeds, the composition of the liquid phase, it will move along the line X1B. That is towards the pure B, and that of the vapor phase, it will move towards Y1M. Vapor will move towards this, liquid will move towards this. At point M, the vapor phase and the liquid phase have identical composition. See the identical composition at this point. Thus, condensing the vapor and distillation, the resultant solution will not yield again any other composition richer in A or liquid richer in B. We will get the same composition. At point B, we will get the same composition. The former can be collected from the top of the column and the latter from the bottom of the column. The similar conclusion, it is related when the composition of the mixture lies between A and M. Suppose we are here. Then again, distillation process, we will be here. Liquid richer in A, vapor richer in B. Vapor will travel this path, liquid will travel this path. Liquid will be collected below the distillation unit and the vapors will be collected in the collector conical flask. But when we reach to point M, we will get the composition. If we reboil or condense, we will get the fixed composition, this one. So, thus we see that fractional distillation exhibits a minimum in the boiling point. So distillate, it is a constant boiling liquid mixture of composition corresponding to the point M, and residue is pure A, not B at all, if the composition lies between A and M. Or if the composition lies between here, we will get pure B and M. we will not get pure A in this case. So it depends where is your composition. If composition rise to this side, we can reach to pure B and this one. If your composition lies to this side, we will get pure A and this one. Now this is about the solution having such type of boiling point. Now come to this type of solution. The same situation and the same explanation, we will see that here also we will get the same things. A liquid mixture of composition X1, suppose this one. Or we can consider X2, this side also. Any side we can consider. Suppose we are considering this. If it starts boiling, the vapor is this, richer in B. And the liquid is richer in A. Thus, during distillation, composition of the liquid phase moves along X1M. We will move along this and the vapor will move along this. So, if we are on this side, we will get the composition of vapor as pure B and this one M. Also, if you are present in this side, then the composition of the liquid will move like this and the vapor will become gradually rich in this. So we will get this one, pure A and this. So we have seen that the liquid mixture of composition M, in both the graph we are seeing the composition M corresponding to minima or maxima boiling point. It boils at constant temperature and it can be distilled without any change in the composition. When we distill, if we boil, condense, means if we distill this composition, then there will be no change in composition. We will get a fixed composition only. The situation is different on both the sides, but at point M, we will get the same composition. So such liquid mixture is known as azeotropic mixture or azeotrops. It is a Greek word having the meaning to boil unchanged. Means after boiling, condensation, distillation, the composition remains unchanged. For a given pair of liquid at a given pressure, the composition of the mixture and the corresponding boiling point all are fixed, definite values. Their value will vary as the external pressure is changed. This is supported by the solution at point M, really a mixture of two liquids and not a liquid containing only one component. It is a mixture of two liquids. Thus, the compound formation at point M, it is excluded here. Now, the lever rule. If a solution consists of more than one phase, the amount of each phase represented by a lever rule. It can be explained by considering a simple balance. The composition of the solution is represented by the fulcrum and the composition of the two phases by the ends of the two bars C1, C2. The proportion of the phases present are determined by the weights which are needed to balance the system. So, fraction of phase 1 is C2 minus C upon C2 minus C1, and the fraction of phase 2 will be C minus C1 upon C2 minus C1. Now, about the binary phase diagram, before any calculation, a tie line, we have discussed this also, a tie line, which is drawn on the phase diagram to determine the mass fraction of each element. It is drawn horizontally at the composition of temperature from one phase to the another. The mass fraction of element at the liquidus is given by these equations, which are calculated by the lever rule. So, by this method, we can find out the compositions successfully. Now, we will study the process of steam distillation. Steam distillation, it is a separation technique. So, here it is primarily used to separate the temperature sensitive organic molecules from a non-volatile component. Organic molecule must be immiscible in water In steam distillation, the immiscible mixture is heated to boiling, causing the distillation of both water and a volatile organic compound. So gaseous mixture travel upward to a condenser, which then condenses back to the vapor to the liquid so that it can be collected. In contrast to the simple distillation, steam distillation uses a water reservoir to replenish water in the heated mixture throughout the process. The immiscible organic compound or component, it is slowly distilled along the water, and while the non-volatile component remains in the heated mixture. Once the organic component is distilled, it can be separated. In an immiscible mixture, where the components form heterogeneous mixture, the vapor pressure of each component contribute independently to the total vapor pressure. So we will see the boiling point of immiscible mixture. As the liquid is heated, vapor pressure increases. Each component in the mixture has its own boiling point. In a mixture of miscible liquid, boiling occurs at a temperature between boiling point of the constituent liquid. Now, this is the apparatus which is used in the laboratory. In this, the condensation can be carried out. The organic mixture is taken together with some water. It is placed in the round bottom flask, which is then connected to a steam generator on one side and a water condenser on the another side. Now we have to heat this mixture to avoid the condensation of the steam. Otherwise, this steam generator, the steam is coming and it can be condensed. So we have to heat this mixture to avoid the condensation. The water in the flask is heated and the current of the steam is passed into the mixture. The low boiling liquid is steam volatile, so it readily passes over the steam. The vapor of the compound along with the steam leaves the flask from outlet and gets condensed in the condenser. It is then collected in a conical flask containing ice to solidify the liquid, to cool the liquid. The pure liquid obtained, it is then filtered by the funnel, and the residue in the distillation flask now contains another liquid. So by this process, the two liquids have been separated. So such are the processes which are used to follow in the laboratory. So this is all about the distillation processes.